let's hope everyone had a fantastic coffee break. And we are going to have 3 more talks before lunch. So our first talk is going to be given by Ian Osband. He's a research scientist at Google DeepMind with a focus on decision making under uncertainty. He finished his PhD at Stanford University under Benjamin Monroy. And today we are going to hear him talk about his work on deep exploration via randomized value functions. Let's welcome Ian.
Thanks. All right, thanks everyone. Thanks for coming. And I start with a thank you slide. Thanks to the DALI organizers, great event on here. And this is work did during my PhD at Stanford with my advisor, Ben Van Roy, collaborating a lot with Daniel Rousseau, Zheng Wen, and with Google DeepMind, and of course, many other people along the way. So I'm going to start with a few impact slides. I'm trying this out as a technique. So if you see pictures, just focus on those slides and maybe take your emails or whatever in between. So this is one of them. Most machine learning and AI focuses on the analysis of big data. And I'm here to talk about the problem of exploration, which is about getting smart data. Okay? So big data versus smart data. What do I mean by that? We're considering a learning system that actually interacts with the environment. So our little robot in the world takes actions and gets data back. And now reinforcement learning combines generalization, learning from big data, finding patterns, all these things. Exploration, that's partial feedback. You need to take the actions in order to gather the data that you need and long-term consequences. And common approaches to exploration can require an exponentially large data set to solve even a very simple task. So although we live in era of big data, we've got faster and faster computers, if you don't have smart exploration, if you don't get the right data, then you're never going to have a data set big enough to solve a meaningful task. And this is a bit of a caricature here, but this is a type of MDP, number of states, and this is the amount of data it takes to learn it. And this is most common schemes like epsilon greedy can be exponential in the number of states. Whereas if you use deep exploration, and I'll say what that is, then you can solve it in a much more reasonable amount of times and scale to bigger problems. So I'll start with just an example, and it's called cart pole swing up. Very simple one, classic control problem, but I've changed it a little bit. You have a small cost for moving. You only get a reward when it's upright and when it's not moving, and in the middle, right? So this is kind of a harder problem. And even state-of-the-art deep RL approaches can be useless in this type of task. Because, and I'll just show you a video now. And I probably got over the 10. It's very dramatic. So we don't have any music, but you can imagine it. Cart pole. So the pole starts down. Normally it starts up. And it's a small cost for moving. And the agent only gets a reward when it's all the way up. And it's in the center. But without deep exploration, or deep space exploration even, you may never see the reward, okay? Now this is a pretty simple problem, right? It's hard to say that, doing cart pole swing up is AGI. But, this is with epsilon greedy, so it's not remaking. But after 500 episodes, it's learning, but it's learning that moving has a cost, and I never see any reward. So just give up, okay? And this is with an annealing epsilon greedy. And after 1,000, after the epsilon has washed out, it just learns to do nothing. It's useless. But all hope is not lost because this mystical approach of deep exploration, which I will on the next slide say what that is. So it's useless when it starts, but it kind of keeps going. 500 episodes, it's sort of all exploring the space much better, trying to learn. It's getting a little bit of reward there, only in the middle, and then failing. But after 1,000 episodes, this approach works really well. This isn't meant to be a super hard problem. This is meant to be an easy problem. But it kind of highlights how existing approaches are kind of missing something.
Are you using fixed epsilon or?
Annealing epsilon over 1,000 steps. So that often makes a difference. So what is deep exploration? Let's imagine that there's this maze, a rat or mouse that's been in the maze multiple times. And it's gathered data about this left-hand side of the maze. But but it's never been to the right-hand side of the maze. The right-hand side of the maze is unknown. But it knows that there's a path out of the maze to get this cheese, right? So this is very easy. I'll go in there, I'll get cheese. It likes cheese. The thing is, there's this whole area of the maze that's never explored. And there could be something bad in there, a mouse trap, or there could be something really good, mouse birthday cake. But the agent doesn't know. And our current approaches say, oh, do the thing which you think is best, which is getting this cheese, and then sometimes try a little bit of exploration. Now, note that doing a little bit of exploration along this path, you don't learn anything. It's very hard to get. You will never, from random search, make it through to this unknown part of the maze, right? In order to learn something, you have to make a beeline to the part of the maze that you don't know, right? And this is something that Shipra just mentioned in the talk before, but this is the thing which we're calling deep exploration. It's that you need to make a concerted effort over multiple time steps to learn something in the future. Now this is the thing which a lot of deep RL or RL algorithms are missing. And to characterize this, we can either be motivated by reward or by learning. Learning is the exploration part. And you can either be looking at the immediate over one action or later in the episode, multiple steps. And deep exploration is when you look for learning later in the episode. When the rat chooses to go right here instead of taking the cheese, it doesn't learn anything immediately. It's taking that action because it knows later in its path it can learn something. So, another freeze frame, deep exploration is an algorithm that can plan to learn. Okay? So that's kind of, this distinction is something I would like people to take away and say, oh yeah, you obviously need that. That's really important, or can be really important. So I guess revisiting this, the talk is going to center around an idea called Thompson sampling, a very simple thing, and it's great to go after Shipra because she gave you a great introduction, but it's one of the oldest heuristics for balancing exploration and exploitation, and it says at a high level, randomly select an action according to the probability that it's optimal. Now this is just going to be the kind of jumping off point for the algorithms which we explore in this talk. Interestingly, there have been a huge amount of very general performance bounds, so regret bounds, how much worse you could do than optimal if you perform it, and I'm just going to highlight one, which I like. So recent work, not by me, but some people I've worked with, and this says your expected regret is bounded by this term after L episodes, square root of L, by a term that involves the information ratio, cost per bit of the algorithm, and the rate distortion, kind of like the entropy of the unknown optimal policy. So this is just a very general setting in which this is a good thing to do. But there are many other state-of-the-art results in specific problems, and to highlight, countless many. So this kind of frames this problem like an active learning problem, multi-arm bandit. I just want to highlight that reinforcement learning isn't really that different from the standard bandit or active learning problems. So in Bayesian optimization, multi-arm bandit, you take an action, unknown function, output, repeat. You can look at reinforcement learning to something similar. You take a policy, you interact with the environment, you get data, repeat. Okay? It's just that a policy or these outputs have a particular structure. The Bellman update, or that there are lots of policies. There are typically far more policies, exponentially many policies, compared to multi-arm bandits, where there's just a single action. So obviously a connection here. So this word deep exploration, I should highlight, if it wasn't clear before, this has nothing to do with deep learning. It's obviously a bit of a catchy title, but it's really the literature on what's so-called efficient RL is also, I guess, the literature on deep exploration. And it says that if you do deep exploration in a good way, then you can bound your regret in reinforcement learning in order of polynomial number of parameters and square root of L. And so, Shipra's talk is the latest in a long line of algorithms that show that if you do deep exploration in a principled way, then you can learn in a polynomial amount of data, as opposed to exponential. But the focus has mostly been on tabular models, right? Independent states and actions. And that's not going to address problems of practical scale, right? It's not reasonable. There are far too many states in the problems we care about. But what it does do is it serves as a sanity check for exploration. If we're trying to make algorithms for artificial general intelligence, shouldn't they be able to solve tabular problems? And if they can't solve tabular problems, doesn't that highlight that there's a problem in our algorithm and we should try and fix it on these simple things before jumping too far forward? Or at least keep it in the back of our mind. Well, this talk is trying to take steps towards a principal and scalable approach for deep exploration. So now, posterior sampling for reinforcement learning, we just had a talk on it, and I guess it's Thompson sampling for MDPs, okay? It's nothing new. You sample an MDP from your posterior, you apply a policy for the entire episode. And I guess what's surprising is that I just highlighted one set of regret bounds, we just had a talk on another, is that in the tabular setting, irrespective of your prior, this is a good thing to do. This thing makes sense. You get polynomial learning guarantees. So this is the horizon of the problem, number of states, number of actions, number of episodes. And so I guess bringing this back to more of the people on the generative side of the problem, we need to be able to sample generative models of the posterior. And if we can do that, then we're going to have efficient exploration from a very simple algorithm. It's not a complicated, there are no annealing epsilon, deltas, whatever. You just maintain your posterior, you sample from it, you follow the policy which is optimal for that sample, and we're done. Now, the question you might ask is, well, does PSRL really do deep exploration? So I'm going to support that in 3 ways. The first is theory. We have a regret bound that's polynomial in SANH. So by the definition I gave before, yes, it does. Computation. When you run this algorithm on actual problems, so this is just tabular MDPs, you compare epsilon greedy or Boltzmann or any of these things versus PSRL, it learns in a graceful way, as the theory would suggest. And the final thing I'm going to try to give you is a bit of intuition. How does this work? We're going to revisit this mouse and imagine that the mouse performs PSRL. Well, in one episode, it samples a random MDP from its posterior, and it says, oh, that's got cheese in there, a trap. I better not go there. So the optimal policy will be to go there. But the next time, it doesn't gather any new information about this area when it does that. So the next time when it comes to sample, it samples the birthday cake. It says, wow, I need to go over there to get that cake. So then the policy takes it all the way here in search of this knowledge. So that's the way in which it does deep exploration. And that's why it can be exponentially better than things like Boltzmann or epsilon greedy or any of these things. Yes, it does. So a question I get a lot, and I've had it a lot, is, well, PSRL, does that do model learning? Does it do policy learning? Or does it do value learning? Okay, well, I guess you could say it does model learning because you could do it by sample from the posterior of the model, then optimize. So that's model learning. But another way you could do it is you could sample from the posterior of the value and then argmax. Well, that's value learning. Or you could sample from the posterior of the optimal policy and then apply that policy. Well, that's policy learning. Well, actually, it does all of these things. At a high level, PSRL is more of an approach, the Thompson sampling principle. You can do it in model policy or value learning, right? And if we do get good generative models in any one of these things, well, then we can apply this principle together and we can get better reinforcement learning. I guess the next thing you want to do is we want to have generalization. Tabular bounds are not good enough. Okay, we need to learn from similar experience. And actually, we have some theory about this. If you have a parameterized model, then you can have statistical efficiency in the size of the model. The problem, so you get a regret bound that depends on the dimension of the MDP. So for linear quadratic systems, it's like D, the dimension. So these are good results. But the problem is that unless it's a very simple problem, solving model-based RL for the optimal policy is itself difficult. You could also do parameterized policies. And actually here, the bandit literature applies almost directly, right? It's the space of policies. You apply this entropy results like you had before or many others. The problem is the space of policies for RL is really huge. So although we get a regret bound in terms of the number of policies, the dimension of the policy class, apart from for specific cases, this could be too big as well. So this talk and this paper that goes with it, that we're submitting to JMLR is about parameterized value functions and viewing this as a scalable approach to approximate PSRL with generalization. We call that randomized value functions to show that it's something like a posterior, but it's not exactly the posterior. And the idea is that you generate an approximate posterior sample for the value function. So you can combine this with any standard value learning algorithm, but we fit it to randomly perturbed data. Okay, this is sort of an inspiration. This is just one approach. This is our approach. Sort of informed by the equivalence in some settings of like Bayes posteriors fitting to random data. And we actually have some theory when you do tabular representations and least squared value iteration. So again, this isn't with generalization, but it's a sanity check. And it shows that if you do this with Dirichlet prior, then you get a regret bound. And that this actually matches kind of state-of-the-art stuff. So at least in the simple cat setting, this algorithm passes a sanity check. That doesn't mean it's perfect, but it's a good start, because Epsilon, Greedy, Boltzmann, they do not. But you can apply this algorithm, even if you don't have the regret bound, to domains with generalization, to LSVI without a tabular representation. And when you do that, we get very good performance on some problems, and it kind of shows you that doing approximate posterior inference, so these aren't real posteriors of the value function, they're just approximate, randomized value functions. But if they satisfy certain conditions, namely that they're spread out enough and they condense with enough data, then you recover this good performance. So what does randomized value function look like? Well, this is your standard value function learning. You get your data, you regularize it a bit. Learning, this is DQN here, LSVI, you get your estimates. Randomized learning is the same thing, but you just judiciously add some sampled noise. And if you do this in the right way, well, then you recover these regret bounds. This is a practical algorithm, because you can just run it with any learning agent. The choice of this sort of roughly corresponds to your prior. But maybe for those of you with a generative model bent, this approach, this is the bit which you would replace by a more sophisticated or more sensible generative model for value functions. And that would be great. I'd love to see that. But another key takeaway here, if you train on noisy data, you get randomized values. And in some cases, the greedy policy derived from randomized value functions can yield intelligent, deep exploration performance, which is kind of surprising. So the algorithm which I said before was not, again, still not quite practical because it involved taking your whole data set and retraining it every time you wanted a sample. Well, our approach to get around that is kind of via generating an ensemble online. You train K models in parallel, you use that as an approximate posterior. And if you want to get a random sample, then you just sample one of these models at uniform and follow that policy. But hopefully this will stir some interest. Maybe we can do something better with structured prediction for value functions. And this is the part where I think you'd fit it in. I want a method that's able to give me posterior samples from a value function of a certain class. Cool. So now revisiting this cart pole swing up. I'm not going to go into too much detail here, but this is what happens if you run it with a tabular encoding, sort of discretizing the space, comparing epsilon greedy versus the random bias value functions versus an ensemble approach. So the difference is night and day. If you run this epsilon greedy, as long as you want, it's never going to learn. But this method really works. Now the same thing happens kind of with a neural network running it. This is an annealing epsilon greedy, and this is DQN with an ensemble of models. So we're able to make practical algorithms that solve this problem of deep exploration with nonlinear generalization. So I know that we started late. I'm kind of running out of time. This is just a bit of a screenshot of applying this kind of approach to Atari games. And this is, call it bootstrap DQN because we use bootstrapping of the data to get the randomized value function estimates. And this is playing a few Atari games, and you can see okay, this is how you play the game Hero. But we're now going to visualize the policy learned by each of the separate Q values. And you're going to see that, in the early part of the game, which they all know, they all basically perform it the same way. But as you get further through the game, they start to explore in more interesting ways. They have more diverse behavior. And I guess we argue that this is evocative of some kind of deep exploration because they do truly different things as opposed to just epsilon greedy on each other. So I know we started late. We're almost at the end. Does this always work? So this is robust, and it really, really works. It's amazing. When you have finite states and actions, and when you have accurate linear parameterizations. So if you want some theory, I've been working a lot on trying to get a theory to prove that this works with linear parameterizations of the value function. So the true value function lies within the span. So empirically, this works amazingly, always works, but don't have a theory of it yet. But I think it's possible. But existing value function learning is pretty flaky. So DQN, anyone who's tried DQN or LSVI even, if you have a misspecified basis, even the underlying algorithm, just for fitting the value function, doesn't work very well. And that leads to poor performance in this algorithm as well. So this is an ongoing area of work. Need to understand how we can do this better. And so I'd like to get you guys interested in this principle of randomized value functions, or I guess Thompson sampling at a high level versus specific algorithms. Can we get generative models for direct sampling of the value function, or policies, or whatever? What would that look like? Specific neural network architectures that are amenable to this type of training. But there is hope, right? And so I think just leave you again with one final impact slide. So robust AI will require deep exploration, and randomization offers a principled and scalable approach to deep exploration. So hopefully I've got some of you guys interested, and if the interest is, oh, you're so wrong, and let me tell you why you're wrong, please come and tell me about it, because it's great. But otherwise, thank you very much. Yes, Shipper.
When you work out the data, you use a specific distribution or just?
I think that in some specific case, we used Gaussian noise that was matched to a certain prior that allowed us to show regret bounds. I think as a more general approach, we were arguing for using something like non-parametric bootstrap because it kind of gets the variance from the data itself. But I think that roughly corresponds to your choice of prior or likelihood function. Yes?
So I keep on thinking needle in the haystack, needle in the haystack.
Right.
And so you say if I distort something in a random way, the value function, then I get policies that some miraculous way get me to needle in the haystack. So is the answer that you assume that you have to be very close, that you have to have very little model mismatch? Is that exactly?
I think that potentially, that's a really great question, and the needle in the haystack thing is often used to be evocative of this. I'm going to try to steam back to just give you an idea that some of these things that seem like needle in the haystack, so this problem here, right? There's this MDP in this model, and the mouse knows it's been to all of these places, but it knows it's never chosen the action right here, okay? So in some sense, you know, the greedy policy, from what it's seen so far, is to just go here. And in that case, getting a series of epsilons that takes you to anything new is a needle in the haystack, right? That's never going to happen. If you say, oh, I do epsilon greedy, you'll never make it there. But it's not impossible to imagine an algorithm that says, oh, hey, I've got very little data here, so I keep my posterior wide. Sometimes I sample something which I think might be good. And then once you do that, it incentivizes you to go there.
Yeah, but the probability to get there is very small.
Conditional on what? It depends. If you sample that you think that they're, you know, imagine you know nothing.
These are random explorations that you make.
So
the space is very big, so the probability that they hit the bounce.
So imagine if the value of this is like 0.1. Okay, and you know that you can get a policy of 0.1, but you somehow inject some noise on your data that's like a scale of 1, because you think that that's roughly the scale of the optimal value function. Well, you have a 50-50 chance of generating a +1 here. If you generate a +1 there, then solving the policy, which is optimal for that +1 sample, will take you with absolute certainty to get there.
Because the picture suggests a maze in which you have to take a whole number of consecutive steps.
Yes.
Which is a half times a half times a half.
So I guess I'm assuming that given its posterior beliefs, or the value function that says, oh, there could be something good here, then your algorithm says, hey, I really want to get there, and you solve the MDP planning problem. Or equivalently, you know, taking argmax of Q, and then that takes you there deterministically, not by chance, but through the process of deep exploration, because you say, oh, I want to get there because there might be something good at the end.
So again, is the miracle here that you assume that your your value function correctly parameterizes the truth out there. I mean, so
I guess in some sense that is true, or if you dig a little bit deeper, it kind of says the miracle comes from if your value function samples span the possibilities of truth. Because it doesn't matter if this isn't actually as good as what you thought it was, because you'll go there, you'll find out. It's just that you don't discount things that are possible.
Maybe just to follow up on this, in this picture, right? I mean, you put the cake into just the right-hand side.
Sure.
This is also a maze, so in reality, you pick a point there which may have very high reward.
Absolutely.
And then you're solving an MPP, you will find a path to that point. But it could be that the real reward is somewhere else in that maze.
Absolutely.
And you still have, I mean, in a way, in the known part of the maze, you are very good and efficiently finding the exit into the new universe, so to speak. But then once you're in that new universe, it's very hard there to do anything super smart.
So that's totally true, and the way that this would work is that it just gets you one step further each time. So sampling this cake imaginary here gets you one tiny little bit further, but doesn't necessarily get you any further. But it's just, well, then the next time you can go one step further than that. And that's how you get polynomial learning instead of exponential learning. Yeah.
So your bootstrap DQN can be seen as a efficient approximation to the Bayesian posterior ensemble in a way, right? So do you think with recent progress in more robust Bayesian neural networks in general, there's something to gain from using a more closer to the Bayesian, full Bayesian posterior technique, like say variation inference? Is there something to gain, or is your intuition that maybe it's not?
No. So I absolutely think that that's absolutely something where there's a lot to gain. So if we can get better estimates and better parametric to reflect our priors or whatever, that's huge. So one thing to be careful of, though, is that if you're just going to, let's imagine you just took your favorite variational inference method for supervised learning, and then you put it in the RL setting, where Q equals reward plus gamma times Q, you might not back up the uncertainty in the right way if you're not careful. Because obviously the uncertainty in the next step Q affects the uncertainty in this step Q. And so you'd have to be careful about that.
From far, this smells a lot like perturbed maps. So I was wondering whether
Yes.
these links there are perhaps also there to use these windable whatever distributions, or does it influence the noise process you should use?
So absolutely, I don't think we've put a huge amount of thought into that. I think that we focused on a simple setting, a Gaussian setting, where we were able to show an equivalence and kind of recover these regret bounds. But understanding the type of structure, the type of noise, the type of sampling for more interesting, richer problems, I think is really interesting. Cool. All right, well, thanks for all the questions, guys. This was really great. See you later.